Next up, Philippe Sucosky, Space and the Heart, a Love Story? Question mark?
Good evening, everyone. So, you've heard it. We are going to Mars. Yeah! This may sound like a joke, but the opening of a space exploration business to private companies and recent technological progress has put us closer than ever to travel to space and colonize planets. But what if space exploration required more than just fancy rockets? There is one aspect of space travel that doesn't make the headlines: its effects on the human body. And there are many of them. In space, for example, the lack of gravity is known to pull the blood from the legs to the head, to shrink the heart, and to reduce the cerebral blood flow in arteries and veins. And we still don't know what the long-term effects of those changes are on human health. So when the first study reporting on the long-term effects of microgravity on blood flow came out, it got a lot of media attention. This study was about performing ultrasound measurements to compare blood flow in the jugular vein of 10 astronauts before they left the Earth and after they spent 6 months on the International Space Station. And the results were quite unexpected. In most astronauts pre-flight, the blood flow was forward, normal blood flow in the veins. But after 6 months in space, this normal forward flow was not detected in any astronaut. Instead, most of them had a forward flow that sometimes returned to zero. Others had an oscillatory flow, so forward and backward at the same time. One even had a reverse flow. Why is this concerning? Well, it's concerning because on Earth, we know that the arterial cells are very sensitive to the velocity and direction of blood flow. This is something that's very obvious in a carotid bifurcation, which is located in the neck. In the arterial wall region that experience high forward flow, the cells elongate. In the wall regions experiencing low oscillatory flow, the cells are more randomly shaped. And what's very remarkable about this carotid bifurcation is that it is particularly vulnerable to atherosclerosis. It's a disorder that consists of the formation of a plaque on the arterial wall that is going to block the passage of blood flow. And guess what? The plaque only forms in those regions that experience low oscillatory flow. So it looks like microgravity tends to make blood flow slower and more oscillatory in veins. But what about in arteries? Well, if the same happened in arteries, it would be a big deal, because we just saw that low oscillatory flow is bad news for arteries. It leads to disease and atherosclerosis. But we still don't know what the long-term effects of microgravity are on the arterial circulation. First, because long-term data in space is still not widely available. Also, because it would be very difficult to measure arterial blood flow in space at a sufficiently high resolution. So in my lab, to bypass those challenges, we designed a computational model to compare arterial blood flow on Earth and in space. And this is how we did this. First, we used ultrasound images from 16 subjects to create 3D representations of carotid bifurcation anatomies. In each image, which is essentially a slice of a blood vessel, we identified the center and the wall of the artery. This helped us generate a wireframe model. And then we just need to add the wall to complete the 3D model. One thing that we had to do also is to split each model into a bunch of tiny volumes in order to run the simulations. We also had to provide the software with the mathematical equations that describe the motion of blood flow in those anatomies. Those are the Navier-Stokes equations, and I can tell you they are a pain to solve. Finally, we also had to tell the software to differentiate blood flow on Earth from blood flow in space. We did this by imposing different flow conditions across the models. So to simulate blood flow on Earth, we use the blood flow rate measured from the subject. To simulate blood flow in space, we reduced dose rate by 18%, and we also cut the gravitational field. So what did we get? First, we compared the blood flow trajectories on Earth and in space at different instants of time during the cardiac cycle. Overall, they were very similar. There were only a few regions where we could detect differences between Earth and space. Those trajectories are kind of nice looking, colorful, but they don't tell us much about what the arterial cells really feel. So instead, we looked at the shear force. And you don't realize it yet, but you all know what I'm talking about here. The shear force is what bends the grass when the wind blows on it. In the blood vessel, it is the force that blood exerts on the cells located on the arterial wall. And because blood flow is pulsatile, that shear force changes at each instant of time. It changes in terms of magnitude, it also changes in terms of direction. So we typically characterize that force in terms of time average magnitude and time average direction over the cardiac cycle. we can calculate those characteristics at every point on the arterial wall. We can even calculate the changes in those characteristics between Earth and space. So when we looked at those changes in each of the 16 models, we actually saw that the results were all over the place. There was no consistency whatsoever between the 16 models. So instead of looking at individual models, we calculated the changes in shear force characteristics between Earth and space, but on average over the 16 models. And we did that in 3 different regions, the main branch of a bifurcation and the 2 other branches. So when we looked at those population average changes, we saw that in space there was a 23% reduction in shear force magnitude as compared to Earth. We also computed the population average change in shear force direction between Earth and space. The simulations predicted that the blood flow was actually forward, both on Earth and in space, and that microgravity had actually very little impact on the direction of the shear force. The problem is that by looking at those population average changes, we were somewhat missing the impact that individual anatomies may have on those changes. So we decided to look again at the changes in shear force direction between Earth and space, but this time looking at the data collected in each individual model. And the results were very eye-opening. We saw that in 3 anatomies, in 3 models, essentially the shear force direction became more oscillatory in space. That was totally opposite to the rest of the model, which all predicted a shear force that was more forward in space. So what this study tells us is very important. It tells us that in most cases, microgravity will only reduce the magnitude of a shear force on the arterial cells without changing its direction. But in 20% of cases, it will actually increase the oscillatory nature of a blood flow. And this, ladies and gentlemen, is bad news for space exploration. Why? Remember, low oscillatory flow is bad for arteries. It leads to disease and atherosclerosis. So here are my 2 cents. Before we design the next rocket or we send the next billionaire to space, let's listen to the heart. Thank you.
He took an extra 5 seconds and looked right in my eyes. But thank you for that, Philippe.